Hello, Assalamu alaikum. I welcome everybody to the second session of the workshop on numerical, jointly organized by IEEE EDS Kuwait Student Branch Chapter, IEEE EDS Bangladesh Chapter, and Solid State Circuit Society. As the first session, our instruction of the today's workshop is Dr. Ahsan Alam sir. He completed his PhD from the University of Alberta on solid state circuits. He is currently working at Ansys Canada Limited as a research and development engineer. His expertise is in the simulation of active photonic devices and developing compact models for photonic integrated circuit simulation. The previous session was an introduction to the various fields of numerical. In today's session, we'll go on to a few simulation setups from scratch. Hope you will enjoy it. Please feel free to ask questions as your interaction will make the event successful. You can either write your question in the chat box or raise your hand. Without further delay, let's start today's session. May we, sir?
Yes, of course. Yeah. Thank you, Samit. Yeah. Yes, definitely. Can you everyone hear me?
Yes, sir.
Okay. Thanks. Yeah. Okay. I'll share my screen and then we can get started. Okay, so let me start the slideshow. So yeah, I guess based on the initial flyers, I hope everyone is prepared to learn about our electrical and thermal solver charge and heat today. And then we will also take a look at the photonic integrated circuit simulator interconnect. So I'll start with the component level solvers first. So heat, and you're also seeing like two other names here, DGTD and 𝗵. So these are all our finite element solvers. So all of them uses finite element mesh, whereas the tools that we saw the other day, FDTD and Mode, they use finite difference meshes. So that's one fundamental difference between these two types of tool sets. And so these particular tools, they have a different design environment. And so in the first set of slides, like we'll just quickly take a look at the design environment and get familiar with how it looks. And then we will take a look at specifically charge and heat. DGTD, as I mentioned the other day, uses discrete Galerkin time domain method to solve Maxwell's equation. In essence, it's a solver very similar to FDTD. However, like it has its own advantages and disadvantages. But for most applications, FDTD is the right tool to use when you're doing an optical simulation. So yeah, given that like we have limited time, I don't think it's not a big deal if we don't go over DGTD for this workshop. There are examples available online that you can always go to and check out the solver. Same goes to 𝗵. It is the counterpart of FDE that we saw the other day. So this is also an eigenmode solver, but it uses a finite element mesh. Okay, so let's get started. So on this one, yeah, as I mentioned, like we will look at the user interface, and then we will see kind of like when you're setting up a simulation and running something in this finite element design environment, like how the workflow goes. Yeah, this slide kind of like mentions the solvers that we have in the finite element tool set. What are the kind of like primary application for these? So it's a single design environment that hosts quite a few solvers. So charge for electrical simulations, heat for thermal. You can use DGTD and 𝗵 for optical simulations as well. So you can perform different types of multi-physics simulations with these single design environment. And so some of the examples would be, for example, modulators, like active devices. So where you need to perform electrical and optical simulation and thermal simulations as well. photodetectors, where you need electrical and optical simulation, thermally tuned waveguides, where you would need to do thermal simulation and optical simulation. And then CMOS image sensors is one example where you would need the charge solver for electrical simulation, although for the optical part, FDTD would be the right tool here. And then other examples would be like metamaterial absorbers, where you would use FDTD for photonic simulation and then heat for thermal simulation and so on. So any type of optical device where you need a multi-physics simulation, whether it's to account for electrical effects or thermal effects, then you would use one of these tools or both of them along with optical tools. In most cases, it will be either FDTD or maybe some solver from Mode. So this is how the IDE looks like. So here we can look at the objects tree, and then you see that it's very similar to what we saw in FDTD. So like there are a few differences. So for example, you can see that you have the materials defined in the object tree, and then the geometry is same as before, like you use different primitives to build your complex geometry. And then since it hosts multiple solvers, so you can add like multiple solvers in your simulation file and perform different kinds of simulation on the same geometry. So some of the restrictions are that like for each type of solver, you can use a single solver element. So you cannot have two heat or two FEM solvers at the same time, one solver at a time only. You can run one simulation at a time, and then since everything transfer data between them, so which makes it easier to do multi-physics simulations. So this is how the entire design environment looks like. It has a more modern look than FDTD. FDTD is our key solver for the Lumerical suite, and so it's a more matured solver, but it also has some legacy interface, whereas the finite element design environment is more modern. So you have tabbed tool strips where you have different tabs to switch between the toolbars. And you have a more advanced 3D viewport where you can look at your 3D structure and rotate them nicely. If you look at the toolbar at the top, you'll see that as you add different solvers to your simulation region, you get different tabs for them, which contain like all the different solver objects that you need to add. And so, for example, and then when you're designing your geometry, you pick the design tab, and then that allows you to create structures and add solvers as well as you need them. It also allows you to import structures from different files. Like, for example, like we saw the other day, that you can import GDS files to import. You can use GDS files to import layouts in your design environment and create 3D geometries out of them. And you can see in terms of material database, you have electrical and thermal material database to use with charge and heat. And then there's optical material database here as well, because you can use them with DGTD and FEM. So the workflow when you're building any simulation in the finite element design environment would be, the first step is that you pick your materials. So that way it's slightly different from when you build a simulation in FDTD or Mode. And then you define your geometry and assign materials to the different geometry parts. And then you define the simulation region, like either the simulation area or volume for 2D or 3D simulations, and then add the solver, like what type of simulations you want to run. And then for each solver, there are like solver specific objects. For example, if you're doing an electrical simulation, you will add doping profiles. Maybe if you're doing thermal simulations, then you would add a thermal boundary condition or a heat source. So for each solver, there are like solver specific objects that you can add. Once everything is done, we will see this. So you can partition the volume. So this kind of like creates the actual 3D or 2D volume area that is going to get simulated. So that gives you a chance to see the exact 3D geometry or 2D area that you're simulating. And then before you run the simulation, there is a check button where you can check for errors, like if there is any missing boundary conditions, or maybe you have defined multiple conditions for the same surface and so on. So you can check those, and then finally you can run simulation. And then of course, it supports our usual parameter sweep and optimization and yield analysis. Those are built into all of the tools. So talking about the material database, as I mentioned, because it has multiple solvers, so it gives you different material databases. And then when you go to the material database, like you pick a particular material database, and then you can choose to add different materials to your objects tree. So only the materials that you add to your object tree, those are available for your simulation. So this way, it's slightly different from what you see in FDTD and mode. And then once you add a material to the objects tree, that kind of like becomes your kind of like material that gets used in simulation. It's not hooked up to the material database anymore. You can open up the material properties right from the object tree. If you can adjust them if needed, and so on. In terms of geometry, in this case, it's very similar to what we saw in FDTD and mode. So you have different primitives available to you, and you can combine them to create complex structures. And then for each of the geometry, you can define different materials. So in this list, you will only see the materials that you have already added in your objects tree, and then they become available here, and you can assign them to different domains of your simulation region. Another thing that's different in the finite element IDE is that you have a simulation object called simulation region. So you can create your 3D geometry in any way you want by combining different geometries, rectangles, triangles, pyramids, or circles, and so on. And then once you have built the entire design, you can use a 3D cube or to define this simulation volume. The simulation can be 2D or 3D. So again, it can be a rectangle or a 3D cube or pyramid. And then you use that to define like how much of your actual geometry you're going to simulate. And there are some very interesting features in the simulation region. For example, in the finite element environment, you can actually keep the boundaries closed, which gives you a rectangular prism type shape, say for 3D simulations, which is the standard. You can also choose the boundaries to be open. So if you keep a boundary open, then in that particular direction, your simulation volume is actually defined by your geometry. So you can imagine that if your geometry is a sphere and you make all of your boundaries open, your 3D simulation volume is actually going to be a sphere. So it's quite different from what's available in FDTD and mode, where your simulation volume or simulation area is always a rectangular prism or a plane rectangle. But in the finite element environment, your simulation volume, like the 3D volume, can have any shape. And then the shell boundary condition is specifically used in DGTD. So in FDTD, we saw that when you want an absorbing boundary condition, you need a PML boundary condition. And the PML boundary condition is actually a thick layer of a certain material that absorbs all of the light that goes in there. So in order to do that with DGTD, you have to use this shell option in the boundary. When you use the shell option in any of the boundaries, the simulation region kind of like adds a buffer layer in that direction, which you can use as the PML layer. And then this simulation region also has a background material option that you can use. So if in your 3D simulation region, if you have any empty area, you can fill that one up with the background material. Okay, so this is the partition volume that I was talking about. So once you have created your geometry and you have defined your simulation region, the next step would be to partition the volume. So there's a button we will see in the design environment that you click, and then it actually shows you the 3D volume that you're trying to simulate. So as I mentioned, if you keep all the boundaries open, then your actual geometry defines the simulation volume. So here you can see that we had a few spheres in our object tree. And then so the simulation volume that you ended up with is actually a sphere. And so this is what you're gonna be using in your simulation. And you can actually pick different surfaces or different volumes on this sphere. So you can see here, like we have a certain volume or domain selected. And then here we have a certain surface selected. And you can actually go through the object tree and select different domains and surfaces and assign boundary conditions to them very easily. So it gives you way more flexibility in terms of assigning different types of boundary condition to different simulation boundaries. And then finally, the check button allows you to check for errors in your setup. So when you click on check, like it opens up a window, and then it kind of like gives you different information, like what type of boundary condition is getting applied where, and so on. And then if there are any warnings, that'll show up here. And so when you see that there are no warnings, that means that now you're ready to run your simulation. Okay, so that was a quick introduction. Let me just quickly open up the design environment so that all of the points that we just talked about makes sense. So here, this is how the design environment looks like. So you can see that we have the script environment here, and then the optimization sweep tools here, the script prompt here, and the object tree here. So these are all very similar to what we had in FDTD mode. The difference would be like up here now you have more solvers available to you. And then if you add a charge solver, you can see you get a charge tab opened up, and then all the simulation objects that you need to do a charge simulation are available here. Again, if you add a heat solver, then you get a heat tab, and then any simulation object needed for heat pops up here. So as we mentioned, like the simulation workflow would be you first add the materials that you need to add. So if we're doing an electrical simulation, you'd go here to the electrical and thermal material database, and then you pick the simulation, the materials that you need. So for example, you may need to add a silicon material. So when you click on create, you'll see that it creates a copy of the silicon material here. Again, maybe we will select oxide and then click create, and then you get a copy of the oxide material here. So I'll just close this now. And then so now since these are added here, you have these materials available for simulation. You can right click on any of these material properties and then go in there, and then you'll see lots of different material properties that we will talk about in the next few slides that we will see. And then adding geometry, very similar. So you add different geometries, and then you can move them. And then finally, the simulation region object, you define the types of boundaries. We can keep this closed for now. And then the geometry, so you can set the extent of the geometry. So if we go to the side view, you can see that the geometry that we created falls inside the simulation region, but then there's some empty region. So this is where, if you want, you can choose to use the background material here. And then I can make my background oxide. So any empty space is getting filled by oxide. And then for the center, I can maybe use silicon to fill this one up. I'll just keep things simple. So I'll just take this one out. And then I have my charge simulation region. I can add boundary conditions, but maybe first I'll just click on partition here. And then you can see that this is my 2D simulation area. And then if I select the two different domains, you'll see that I have one domain here, which is filled up with silicon. And then I have my domain 2 outside, which is filled up with silicon dioxide. And so this is the 2D area that I'm going to simulate. And then, as I mentioned, you can select the individual surfaces. And then when you apply a boundary condition, you can apply it to any of these surfaces that you want. So lots of flexibility that way. Okay, so let's close this for now. And then I'll go to my next set of slides. So now we will learn a bit more about the chart solver. So we will take a quick look about at the solver physics, and then kind of like the simulation objects. So the specific material models that are available for electrical simulation, the properties of the solver object itself, boundary conditions, doping profile generation, mesh generation, and so on. So as I mentioned earlier, the chart solver is designed to perform electrical simulation on semiconductor devices. So when it comes to commercial electrical solvers for semiconductor devices, the industry standard is drift diffusion based models, and that's what charge uses as well. So it uses Poisson and drift diffusion equations, solves them self-consistently to give you information about the charge density inside your semiconductor materials and how that charge is flowing. So in order to aid you in creating your simulation design, it has semiconductor and semiconductor alloy material models in the material database. And then you can also have different simulation objects and boundary conditions to add electrical and optical stimulus to your simulation volume. And as I mentioned, it uses a finite element mesh. And then the mesher automatically generates an arbitrary finite element mesh and refines it. And then we will see more information about that going forward. Here are some of the applications where chart solver gets used. So CMOS image sensor, where you would use it along with FDTD. Photodetectors, here also using the chart solver along with FDTD allows you to model germanium photodetectors or 3.5 photodetectors. Electro-optic modulators, terahertz resonant modulators, solar cells, MOSFETs, so electrical only simulations as well. Now, a little bit of details about the solver physics. So as I mentioned, in the chart solver, we solve drift diffusion equations. So here you can see the equation for the current density coming from electrons and holes. And then you have one component giving you the current coming from drift due to electric field, and then the other one giving you the current flow coming from diffusion because of the change in density of the carriers in different locations of your device. And then these two combined gives you the information about like how much current is flowing with electrons and holes. At the same time, you also solve electrostatics by solving Poisson's equation. And then finally, you solve the continuity equation to make sure that the total number of charge in the system is conserved. So this is where you account for the fact that you have recombinations happening in the system. And then you also can have optical electron hole pair generation due to optical stimulus. So for example, this is something that you need to account for if you're simulating like a solar cell or an image sensor where you are absorbing light and you're generating electron hole pairs, and that's how this enters your system, the whole system that you're solving. So again, kind of like to summarize, chart solver uses drift diffusion based simulation techniques. It offers both steady state and transient analysis. It also has a small signal AC solver. And then in terms of inputs, your inputs are gonna be your material parameters and your geometry, as well as your electrical and optical stimulus. So you apply a bias voltage, or you apply a generation or optical generation object that introduces electron hole pairs in your volume. And then finally, as results, some of the things that you can see would be, let's say, the electric field profile inside your device, the charge distribution and transport, and some other insights like where you're getting recombinations and how much of recombination are happening in different locations and so on. Oops. Okay, I just realized that I didn't go into slideshow mode here. So again, this is the charts tab, but maybe we can take a closer look now. So when you're doing a chart simulation, these are some of the things that are available to you. So on the very left-hand side, the constraint object is something that's very useful. So when you run a simulation, the first thing the solver does is it generates a simulation mesh, a finite element mesh. However, when you're running a simulation, there could be certain regions where you want the mesh to be finer because maybe the charge is varying really fast there, or there's like some phenomena going on that you want to capture very accurately. And you can put a mesh constraint in that volume or area and then make the mesh finer than it normally would be. So that's what the use of, that's where you would use this particular simulation object. Doping profile is obviously something very important when you're designing an electrical system. So you have like different types of doping objects available. These are all analytic doping objects. There's also the import doping object that allows you to import a doping profile from somewhere else. So if you have some doping profile from a process simulator, you can import that. If you want to create an analytic doping profile by running some code in MATLAB or something like that, and you have a 3D profile, you can also import that using the import doping object and then bring it into your simulation. In terms of boundary condition, it's pretty straightforward. You have the electrical boundary condition to apply voltages at your different electrical contacts in your geometry. And then you have surface recombination to model recombination at material interfaces. So for example, the interface between your silicon and oxide, you always have lots of traps there to trap the charge, and those are like centers for recombination. And so you can model those using this boundary condition. In terms of sources, you can have optical and heat sources. So the optical sources are your way of bringing information about optical absorption from FDTD. So as I mentioned, if you're doing simulation on a CMOS image sensor, you start by doing an optical simulation and you figure out how much of the light is getting absorbed. And then in FDTD, there are analysis objects that calculates the amount of electron hole pair generation from the optical absorption. And you can bring that information directly into your charge simulation through this import optical source. And so when you bring that information into your electrical simulation, your device will get electron hole pair generated inside them based on the optical absorption that you simulated in FDTD. The heat source is used if you're running an electrothermal simulation. So one advantage of having charge and heat both in the same design environment is that you can couple them together and then you can run electrothermal simulation. And so when you're doing that type of simulation, you can have a heat source to introduce some thermal input to your device. And then you will see that the temperature is changing and then the behavior of your electrical device is changing. So that's something that you can model. And then you can also import a temperature map to give your device some predefined temperature and so on. In terms of monitors, there are different kinds of monitors. So you can capture the charge density profile inside your device using this one, the electric field profile, band structure, current density, and also if you're doing electrothermal simulation, then maybe you're transferring a lot of current through your device, and that's heating it up due to Joule heating. And so you may want to put a temperature monitor on top of your device and capture the temperature map as well. And then finally, you have some buttons to do the different simulation actions. So for example, partition button would create the partition volume, that other plot that we saw, which shows you exactly the volume or area that you're going to simulate. The mesh button allows you to calculate the mesh and then see how the finite element mesh looks like. And then the run button to run the simulation. Okay, so now going into the material database. The material database comes pre-populated with most of the common semiconductor and semiconductor alloys, and some conductors and insulators, so that you can just start to use them in your simulation. One thing to keep in mind is that since the focus of the drip diffusion solver is transport in semiconductors, the conductor models that get used, they are always treated as perfect conductors. They are like pretty straightforward simulation objects that get included. So no electric field inside the conductors, and you simply apply your bias to that. Like you either ground the conductors or you apply a voltage to the conductors, and they the main place where they get included is when you're solving the Poisson's equation. They define the potential boundaries. Insulators are also considered as perfect insulators, so there's no presence of charge inside them. And again, like they're basically used in the when you're solving the Poisson's equation for the electrostatics. And then the semiconductor and alloys are kind of like the key material models that get used, because that's where all the interesting things are happening. The charge density is captured within them. The carrier transport happens inside them. So the semiconductor and semiconductor alloys have very detailed material properties, as we will see. So the semiconductor materials in drip diffusion approach are defined by an effective mass option. So you have for every semiconductor materials, you define an effective mass and then a certain band gap, and that gives you information about their band profile. And then in terms of carrier transport, you define a mobility for electrons and holes. And then there are like different models available so that you can adjust your mobility based on doping level and then applied electric field and so on. And then another important model that gets used are the recombination models. So the trap-assisted, Shockley-Ridgel recombinations, 𝐂𝐴𝐻 recombinations, radiative recombinations, impact ionization if you're trying to model an avalanche photodiode or breakdown in your device. So these are some of the models that are available, and there are like different, I guess, additions to those models that you can also use. Oh, sorry. I just have to quickly sign in here.
Sir, we can't hear you.
So, okay, going forward. So yeah, as I mentioned, as you pick a certain model, for example, here we are looking at the Shockley-Ridgel model to include the carrier lifetime in our simulation. So the carrier lifetime can depend on lots of different things. For example, it depends on the doping level and other stuff. So you have some, and temperature, for example. So you have different analytic models available inside that you can use to vary the carrier lifetime as a function of doping or temperature. Okay, so now we're looking at the property editor for the chart solver. So you can see there are different tabs available. So the first tab is where you define one important parameter called the norm length. So if you're doing a 2D simulation, then you're running your electrical simulation on a cross section. However, once you have run your simulation, the simulation results, for example, the current that flows in your device is given in terms of absolute unit of ampere. So what that means is that the solver assumes a certain length for your device in the third dimension. And that's something that's defined in terms here in norm length. By default, it's set to 1 centimeter. So when you're running simulation on a cross section of your geometry, always keep in mind that by default, the solver would assume that your device is 1 centimeter long in the third dimension. And of course, you can change this value, and if you know the length of your device in that other dimension, you can just set it to that value, and then that way the current that you get from your simulation would be for the actual length of your device. You choose the solver mode here. So by default, it's steady state, but you can choose either transient mode or SSAC or small signal AC mode from here. And then in terms of temperature dependence, by default, you run an isothermal simulation. So like the entire volume has a fixed temperature, which is 300 by default. You can also run non-isothermal simulation where you can import a temperature map, and then that defines that gives your simulation volume a non-uniform temperature. Or you can choose a coupled option from here that allows you to run a coupled charge and heat simulation together. The mesh tab allows you to control your mesh. So this is where you can make your mesh finer. You'll see there are 2 parameters, the maximum edge length and the minimum edge length. So when you're calculating your mesh in charge, it first creates a very coarse mesh. And then the maximum size of that mesh is defined by this number here. And then it breaks down the meshes to make them finer slowly. And the way it does that is it looks at your doping profile, and it has some built-in algorithm inside that it doesn't allow the doping to vary rapidly over a single finite element, like a single triangular or tetrahedral element. So the doping cannot change very rapidly. And if your doping is changing rapidly somewhere, then it'll automatically break down the mesh and make it finer so that the variation over a single element is not too big. And so as it breaks down the mesh and makes the elements, triangular elements, smaller and smaller, you can set a limit as to how small you want it to be. And then this is where you define it. So this parameter is usually more important, where by this you can control what would be the finest mesh that you get in your simulation volume. And then another important parameter here is the maximum refined steps. So as I mentioned, it starts with a coarse mesh, and then it makes it finer and finer in an iterative process. And so there is actually kind of like a safety step here, that it will stop that iteration after a certain amount of steps. And this is because, like, if you have a really big simulation and maybe because of some error in the setup or because of some issue in the solver, it might go into an infinite loop and just blow up your system memory because it's just trying to refine the mesh over and over. So this is kind of like a check that it will automatically stop after a certain number of steps. However, I mentioned this because when you're trying to simulate a big volume, often the iteration, you need a lot of iteration to get a fine enough mesh and a proper mesh. So sometimes you may hit this limit. And then if that happens, you will see in your log file after the simulation that there is a warning. And the solver is telling you that it hit this maximum refined step limit as it was refining the mesh. If you see that particular warning message, then that tells you that it actually hit this limit and your mesh may not be refined properly. And then in that case, you will have to increase this number. Okay, so the small signal AC tab obviously allows you to set up your small signal simulation. So the way the small signal solver works is that you first run a steady state simulation. And then at that point, you assume that your system is linear. And then you you do some perturbative simulation to figure out what is the response of your system to an AC input. So you simply define the amplitude of your perturbation. By default, it's 1 millivolt. And like changing this doesn't really matter because you're assuming your system is linear at this point. So if you just scale your voltage here, the small signal current that flows is just going to scale linearly. So you just ideally set this to a small value. And then you can either do a single frequency small signal analysis, or you can do a frequency sweep. And then you define your start and end frequency. and number of points, and then it'll run a small signal analysis that way. In terms of boundary condition, as I mentioned, the most important one is the electrical contact boundary condition. So this is the one that you use to apply a voltage to your design. And so when you apply this electrical contact boundary condition to a geometry, that geometry always behaves like a perfect conductor. So usually you would apply these two metal domains, which are defined as perfect conductors anyways. But just keep in mind, if you apply an electrical contact boundary condition to a semiconductor rectangle, for example, then that rectangle will start to behave like a perfect conductor as well. Because when you apply an electrical contact boundary condition to a certain domain, we actually apply the voltage boundary condition on the surface of that object. And inside that object, electric field goes to 0. So it actually works like a perfect conductor. And another restriction is that if you have metals in your simulation region, you have to apply an electrical contact boundary condition to that metal. Just because like we do not model any transport inside metals. So they're only used as boundary conditions in your simulation. Another thing to keep in mind is voltages are relative, right? So if you have multiple contacts in your system, then keep in mind that like it's all relative. So ideally you would have a contact set at 0 volt, which will act as your ground, and then any bias that you apply to the other contacts are going to be relative to that ground. So when you're defining the electrical boundary condition, you can either keep a steady state for steady state simulations. You either apply a fixed value, or you can sweep your voltage. And then you can also choose to apply the small AC signal to a particular contact. So for example, let's say you have a PN junction, you have two contacts, anode and cathode. When you're doing an AC analysis, you enable the AC analysis in your chart solver, but then in the contact also, you have to enable this option, this apply AC small signal option. You have to set this to either all, which means that if you're doing a bias sweep, then at every bias point, it'll perform an AC analysis at this contact. So it'll apply the small perturbation on this contact and then calculate all the AC, small signal AC properties. And then there are like two different options. You can either choose all to do it for all bias points, or I think the other one is last. So in that case, like it'll do the bias sweep if you have one, and then it'll just calculate the AC analysis at the last bias point. Similarly, when you're doing transient simulation, you can choose to apply a transient boundary condition. So this way, you can choose to apply a voltage to your system that's varying with time. So here you can see that the input is a step function starting at 0 and then going to 0.2 at 1000 femtosecond and staying at 0.2 for the rest of the simulation. When you're doing a transient simulation, this is how you define how long your simulation would run as well. So the largest time that you have defined in your boundary condition would determine like how long your transient simulation is going to run. And then the other boundary condition is applied at interfaces. So the surface recombination boundary condition, you usually define it at a semiconductor-conductor interface or semiconductor-insulator interface. And the way you define the surface recombination is you define a surface recombination velocity. So higher the velocity, the more recombination you get at an interface. So this slide kind of like shows you how you define, how you apply your boundary condition to your simulation. So you can apply a boundary condition to a full domain. So kind of like a part of the volume of your simulation or area of your simulation if you're doing a 2D simulation. So you can apply a boundary condition to a domain or the surface of a domain. You can apply a boundary condition to the boundary of your simulation region. You can also apply it between the interface of two objects. So for example, the interface between your simulation edge and a particular domain. So that would be like one example. So as I mentioned, like there are quite a lot of flexibilities in terms of how you define your boundary condition and where you apply it. And so this kind of like shows you all the different options that are available. So you can apply it to an entire domain, to a particular surface of a domain, or even kind of like some specific surface that are common between two different domains and so on. So the next step is doping profile. Anytime you're doing an active device simulation, you'll of course dope it. Most of the electrical devices that we use in photonics are based on PN junction devices. So you need at least a P-type doping and an N-type doping. And so one thing to keep in mind is that the doping objects only get applied to semiconductors. Even if you put a doping object on top of metal or an insulator, it won't introduce any charge in them. Just because when you're doing a drip diffusion simulation, we don't keep track of charges inside any material except for semiconductors. Another thing to keep in mind is that the doping objects, if you apply multiple doping on the same volume, the doping values add up. So they're additive. And then the N-type doping and P-type doping have opposite charges. So if you add two N-type dopings on the same volume, the total number of like the final number for doping would be the sum of the two. And then if you apply an N and P-type doping, then the final doping would be the difference of the two. Let's see. And then I guess for doping profile, for some of the doping objects, for example, say if you're defining a constant doping object, it actually behaves like a geometry object. So it has a 3D volume, and then you can define the X, Y, Z span for it. And that's very similar to how you would define a rectangle. And with any geometry that falls inside the extent of a doping object gets doped by that doping object. And then instead of using its own volume, you can also assign a doping object to a particular domain or a particular geometry. And then that entire domain or geometry will get that particular doping value. So you can dope something using that option as well. So here are like different types of doping objects. So one is a constant doping object. As I mentioned, you can design it like a rectangular prism. So you can give it an X location, Y location, Z location, and some span. And then whatever falls inside that volume gets doped. And then you can define the type of the dopant and the concentration. You can also use this drop down to select a particular domain. And then in that case, only that particular domain will get this doping applied to it and nothing else. The other doping object is diffusion doping. So the concept here is if you're diffusing your dopants into your simulation geometry, then this is the dopant type that you use. And so you introduce a peak concentration value at the top surface, or you can actually define like which surface you're introducing your dopant to. So here upper Z means if you have a 3D volume, then let's say the top surface, that's where the peak concentration is getting introduced. And then that peak concentration can go into the device for some distance that you define here using the junction width. And then finally, that it will exponentially drop to a low doping concentration defined by this reference concentration. And then you can either use an error function or a Gaussian function to define like the shape of that descent there. Let's see, yes. So this picture will actually maybe make it easier to see how the diffusion doping object works. So this green box is the 3D rectangular prism that defines the extent of your doping object. And then let's say the positive Z side is where you're introducing the dopants. So the peak concentration that you define would be like the maximum concentration at the top surface here. And then the junction width is, let's say this, if you imagine this other rectangular box here, the edges of this box is junction width amount away from the edges of the actual doping box. And this center box will have a constant high doping concentration defined by your peak concentration. And then from the edge of this center box to the outer box, your doping will drop exponentially, either by using that error function or Gaussian function. And then it'll go from that peak concentration to down to the smaller reference concentration that you define. And so that's how you can have kind of like a peak concentration on the top surface and then exponentially decaying doping as you go inside your device by using these type of doping objects. The other type of doping object, which is more realistic, is implant doping object. So in most cases, when you're doing a CMOS process, let's say, and creating a silicon-based device, and you are introducing dopants, it's more common to use ion implantation. And so in this type of implantation process, the doping profile has a unique shape that you cannot really achieve using the diffusion doping object. Primarily because in this kind of ion implantation doping profiles, your peak concentration happens a little bit inside the top surface. And so the implant doping object actually allows you to capture that kind of shape. And so the way you use this particular doping object is you have a mask opening defined by this green box here. And then you can define like what is the opening of this mask and where it's located in your simulation volume. You can even define like the angle of ion implant. So the angle at which the ions are coming in. So that's kind of like defined here, the type of the dopant and the peak concentration that you will have in your profile. And then you kind of like define a 1D doping profile as the implant goes inside your simulation, your geometry. You can define how the 1D doping profile looks like. You can use either a Gaussian function or a Pearson-4 distribution, which is more appropriate for ion implantation. And so when you define a Pearson-4 distribution, there are like some attributes to the distribution that you can define to make your doping profile very realistic. So I believe I have some slides here. Yes. So as I mentioned, you can either pick a Gaussian or a Pearson-4 distribution. And then these are some of the parameters that you use to give your, make your profile more accurate. So you can define a range, which defines how far away the peak is from the top surface. So for example, here in this picture, range defines like where your peak is located from the surface. And then straggle means how wide the opening of your doping profile is. And then if you're using the Pearson-4 distribution, then you also have skewness. So how skewed is your profile? Is it balanced, or if it's skewed to one side? And then also kurtosis, that kind of like defines like how, like as the profile gets widened, like it also whether it becomes flat or not as it goes away from the peak. So using these four different inputs, you can define a doping profile very accurately. So if you know what your doping profile looks like to start with, you can create it very accurately. There's also another parameter for lateral scatter. So as I mentioned, like this profile gives you a 1D doping profile going inside. And then as you apply this doping profile in your object, and then you do some thermal annealing, the dopants will spread inside the device. So we don't really have a very good analytic model for that. But the way you can mimic this behavior and get a reasonably accurate doping profile in the end is by using a lateral scatter distance. So the value that you provide here, the solver would use a Gaussian distribution and spread the dopant in the lateral direction to give you a more diffused doping profile in the end. So this shows the geometry tab for your implant doping object. And as I mentioned, here using these coordinates, you can define the mask opening. And then using these XYZ coordinates, you can choose like where that mask is located, like how high up from your geometry is the mask opening located. And then finally, we have the import doping object. So as I mentioned, if you have a doping profile generated from elsewhere, either in MATLAB or some other sources, you can import that data into charge through this object. And then this will bring like an entire doping volume inside charge that you can apply on top of your simulation object. Okay, so now coming to sources, optical generation rate, as I mentioned, it allows you to import optical generation rate from FDTD. So if you're simulating a CMOS image sensor or a solar cell, you calculate the optical absorption and then you bring that information over. There is also a delta point generation source. So it introduces a electron hole pairs in one single location inside your simulation volume, and that has some specific application. In terms of monitors, we have charge monitors, electric field monitors, band structure monitor, and current flux monitors. The use is obvious from the names, I believe. And then so this is the mesh tab. Okay, let's see. Okay, so this one is, yeah, I guess we talked about this one already. So here is a sample of the mesh that gets generated in a 2D simulation. So you can see that it starts with a coarse mesh, and then depending on your simulation region and your doping profile, it refines the mesh in different locations. So one thing is to keep in mind is that it refines the mesh more in semiconductors compared to insulators. So in this particular design, we had oxide here, which makes the mesh coarse here, but these are silicon, so the mesh is finer. And then here we have a PN junction, so the doping changes from P-type to N-type, and so you can see the mesh getting refined where the doping is varying very, very sharply. So these are kind of like highlighting those facts. So if you have a material interface, so here we have a metal and a semiconductor interface, so the mesh gets refined there. And then so the mesh is more refined inside semiconductors or active domains. And then as you have a finer mesh in some region and coarser mesh in another region, the mesh will automatically switch from finer to coarser very quickly. So this allows you to have an overall like smaller number of grid points, but still have a fine mesh in regions where you need it. And then this one is the higher refinement in the mesh due to changes in doping density. And then, yeah, you can use the run button to run the simulation. So when you run the simulation, the solver first calculates the mesh and then runs the simulation, and then it saves the result that you can view them. So the results that, so this is one other thing that's different in the finite element solvers compared to FDTD and mode is that once you have finished running your simulation, in FDTD and mode, you actually have to use monitors to record the results. In chart solver, heat solver, the solver objects already reports a lot of the results that you need. So some of the results that the chart solver reports are, for example, the band structure band profile of inside the semiconductor is reported automatically. The charge density is reported. The doping profile is reported. So once you have run your simulation, you can view the 3D doping profile and make sure that everything looks okay. Electrostatics, giving you the electric field and the potential profile. You also can see the carrier mobility. And because carrier mobility is a function of, say, electric field and materials, so you will see like where in your design, like what is the mobility of the carriers at different locations. You can also identify where recombinations are happening. And then finally, at the context, like it'll report you the current as a function of voltage. And then of course, like there are monitors as well. So if you place some monitors in your simulation volume, then you'll get results in the monitors as well. And then the way you view the results is very similar. Wherever you have results available, you right click, click on visualize, and then you pick the results that you want to visualize, and then it'll open up. So for example, here we can see the charge density. So you have two attributes, N and P. So if you click on N, it shows you the electron density profile. And then if you click on P, you'll see the whole density profile. And then and down here, you have the parameters window. So if you did a bias sweep, the independent variable in your plot shows up down here. And then you have a slider. So you can slide this slider to different bias voltages, and then this N and P plot will get updated. Okay, so now it's time for an example. Let me open up charge again. Okay, so I think like the one feedback from the other day was that the comment was it would be helpful to see a simulation setup from scratch. So I will try to create a simulation of a PN junction phase shifter from scratch, and then we will run the simulation and we will look at some results. And so hopefully that way it'll show you how to set up kind of like all the different stages of your simulation and run the simulation and collect results. So here we're gonna first create, well, I guess we'll first add the materials that we need. So those will be the two materials that I added earlier. So silicon for my waveguide, and then I'll have oxide in my wafer, and then oxide cladding on top of the silicon waveguide. So I'll need oxide in my simulation as well. And so I'll just add these two. And then if I want to just double check the material properties, I can go inside. And then you see that silicon is a semiconductor. And so it has an effective mass, a band gap, it has mobility, and then it has the typical recombination models enabled. Impact ionization, band-to-band tunneling by default are disabled because for most simulations, you don't care about them. Only when you're driving things in very high electric fields and you have a carrier multiplication happening or breakdown happening, then you want to enable those. Otherwise, they're usually turned off. And then if I right click on silicon dioxide and look at the properties, you see that it's an insulator. And so the only place where it gets used is when you're solving Poisson's equation, and it's defined by its dielectric constant. So those are my materials. And then now I'll add my geometry. So I'll create my waveguide by using rectangles. So let's go to the side view because we're just going to do a 2D simulation on a cross section. And then so I'll set up my waveguide. Let's say I have 500 micron wide waveguide with 220 micron span, like thickness. And then the Z span would be, okay, I guess that's my Z span. And then the Y span is into the monitor. So I can just set that to any value I want. So I guess I'll just keep that to 100 micron. Oh, sorry, I think I'm making this too big. So it should be 500 nanometers, so 0.5 micron. And then let's say 0.22 micron, which is 220 nanometer. So that's more realistic. So if I say, okay, so that's kind of like my waveguide. And so since this is a PN junction, we actually need a rib waveguide, not a strip waveguide. So we will need to add a silicon slab so that we can add contacts on the two sides and apply voltage to it. So I'll add one more rectangle here. And then this time I'll make the X span much bigger so that it extends outside, and then I can put contacts on the outside. So this one I'll make, I don't know, let's say 2.5 micron long. And then in terms of thickness, I'll make it 0.08, so 80 nanometer thick. And then the Y span, I'll keep it the same. So what did I set it to before? Okay, because it doesn't really matter. So this is my center waveguide. This is my slab. And then I'll just align them properly. So I'll just make sure that my Z span goes from, let's say 0 to 0.22. And then same for the slab. So let's say it goes from 0 to 0.08 micron. So now by combining these two, I have my waveguide defined. I still have to fill them up with silicon. And that's my waveguide. So now I have to add my oxides. So again, I'll put one more rectangle here. And then even though I could ideally use two different rectangles, one to define the oxide at the bottom, and then another one to define the oxide at the top, one easy way that I can make this happen is I can simply choose to I can just simply make this oxide layer really big so that it goes on top and bottom of this silicon. And then so this will give me oxide everywhere. And then as I mentioned earlier, in the first day, is that when you have overlapping geometries, the way you make sure that something takes precedence is by the mesh order. So this one, we will use silicon dioxide because it's our oxide, and then we will make the mesh order larger so that it has lower priority. And so if I set this way, then my silicon will have priority over my oxide. And so the silicon will not get deleted by the oxide rectangle surrounding it. So that should be enough for my geometry. And then next step would be to define my simulation. Okay, and then I need my contacts. So let's put two more rectangles here. So this was my oxide. And then I'll add my anode and my cathode. And then I'll put anode on one side and cathode on the other side. So anode will start from 0.08 to, we'll just make it 1.08. And then it's on the extreme left. So it'll go to minus 1.25 to, let's say, -1. This one. Okay, so location-wise, it's fine. So I forgot to add a metal in my simulation region. So let's make our contacts made out of aluminum. So I'll add an aluminum in my simulation region. So that's my metal for the contact. And then if you go into the properties here, you'll see that it's only defined by work function, because that way, when you're doing a simulation, you have a Schottky contact between your metal and your semiconductor, the solver will use the work function to create the band bending at that interface. So now that I have aluminum here, I can go back to my anode, and then I can fill it up with aluminum. I think the height is a bit too much. We can maybe make it a little bit shorter. Okay. And then to make my life easier, what I'll do is I'll just make a copy of anode, and then I'll call it cathode. And then I'll just take it to the other side. So instead of at -125, we'll just locate it at +125. Okay, so now I have my silicon waveguide, I have my anode, I have my cathode, and then I have to make my simulation region big enough so that I'm covering all of them. So now the simulation region defines what I am going to simulate. So I'm doing a 2D simulation. So I have a 2D Y normal simulation region here. So I'm simulating on the XZ plane as a result. I'm going to keep all the boundaries closed so that this rectangle actually defines the volume or the area that I'm simulating. I don't really need a background material because you can see that everywhere I have either silicon or silicon dioxide. So the background material is not necessary here. So what's necessary is the geometry. And so I'll make my X span, let's say 2.4 micron wide. And my Z span, let's say 1.5 micron. Okay, it's fine. I'll just make my Y oxide slightly bigger so that there's no empty space anywhere. Okay, so that should be my simulation region. So in order to just make sure that everything looks fine, let me first add the charge solver region here because I'm doing an electrical simulation. And now if I just click on partition, it'll actually show me the volume that I'm simulating. And so you can see that I have an oxide domain down here, another oxide domain up here. I have silicon, silicon. These are all silicon. And then I have silicon. Okay, so new material and new material. So these should be the aluminum. So I have to fill them up with aluminum, I guess. Let's see. So this one I filled up with aluminum. And then cathode is also aluminum. Okay. So I wonder when I click on partition, these things should fill up with aluminum. Okay. It's weird. Okay, let me take these ones out. So the preserved surface option is useful if you're merging different geometries together and you still want to keep the surfaces in between them intact, then you keep the preserved surface option enabled. However, like for this particular simulation, I don't really need that, so I'm taking them out. And just to see if this error also goes away. Okay. So now if I partition again, something going on. Okay, so I'll just save the file first, just to make sure that everything is working fine. Let's see. Example, phase shifter. Then let me just open up the file again to see if that helps. Okay, so for some reason that helped. So now if you look at my simulation region here and look at the different domains, you can see that I have domain 1, silicon dioxide, domain 2, aluminum, which was my cathode, silicon waveguide here, another silicon dioxide above, and then finally my anode, which is also aluminum. So that's my simulation region that I'm going to simulate now. And then so before I run the simulation, the last thing that I have to do, or like the two last things that I have to do is, one is set my charge simulation region and then define boundary conditions. So for my charge simulation region, let's see, we're doing a 2D simulation, and then my norm length is set to 1 centimeter. I'm doing a steady state simulation, isothermal at 300 Kelvin, so everything is fine. In terms of mesh, we can start with the default. I'll actually make the mesh even coarser so that it runs faster. And then we're not going to worry about these because we're just doing a steady state simulation. And then we'll define our doping profiles. So I'll add boundary conditions here. And so let's keep things a bit simple. So we will just use some diffusion doping here. And so now I will add some N and P dopings. So I'll use an N++ doping object for my cathode to dope the contact below cathode. And so I'll place it at the extreme right, which I believe was 1.25. So I'll just extend it slightly. Minimum would be, let's say, 0.8. Y can be 1 micron long, and then the Z span would be from the top surface of this layer to I'll just push it below the silicon slab here. So my max would be 0.08, I believe. And then the minimum would be, I'll just push it down by, I don't know, minus 0.1. So that should be the extent of my N++ doping. And then it's N-type doping getting applied from the top surface, so upper Z. The junction width, as I mentioned, the doping remains constant from the top surface up to a certain depth. And then within the junction width amount of length, it drops exponentially. So my Z span is 0.18. And then I want to keep the doping constant throughout the depth in most cases. So what I'll do is I'll make my junction width really small so that I basically have a constant high doping in most of my simulation box or my dopant box. So I'll make this one, let's say 0.01 micron. Distribution function, I'll just make it Gaussian because we just have a 1D doping profile here. It's a doping at the contact, so it should be a very high doping. So I'll just make it, I guess 1E20. And then the reference concentration is just a small value. So now you can see that that's my doping box. And then so it'll give me a very high N-type doping concentration at this contact. So I'll just have to copy this on the other side now to have my P doping. So I'll just copy this one to make my life easier again. Do a P++ type doping this time. Bring this to the other side. So I'll just center it at minus 1.05. And then I'll make sure that it's a P-type doping this time around. Right, so that's my cathode, that's my anode. And then now I need 2 more doping objects to dope my waveguide. So again, I can probably just copy these and then I'll call them N and P. Okay, so now looking at N, I'll just make it bigger. So I'll just make it go up to 0. And then to make sure that I'm doping the top part of the waveguide here, I'll just bring the max up to 0.22. And then since in the waveguide, I'm gonna do a lightly doped compared to the contacts, I can make these 1E17, let's say. So now that's gonna be my doping for the rest of the waveguide on the cathode side. Now remember that doping is additive. So on the cathode side, you can imagine that in this box, my net doping would be the 1E20 coming from the N++ plus the 1E17 coming from the N doping. However, like the second doping value is so small compared to the first one that in essence, like the doping here will still be almost 1E20 per centimeter cube. And so I'm just going to do the same for the other side. So again, for the P doping, I'll make the max here 0. And then I'll push this one up to 0.22. And then I'll make these 1 is 17, let's say. Okay, so that defines my doping on the anode side as well. So now I have p doping on one side, n doping on the other side. So I have formed a p-n junction. Now, just to give you a kind of like the explanation why I'm doping this waveguide with p and n doping is because we are trying to simulate an electrical phase shifter. So the way these devices work is you have this waveguide, and so this waveguide has particular refractive index and light goes through it. And as light propagates, the phase of the light changes based on the effective index of the optical mode. Because you have a PN junction here, so you have a depletion region formed at the center of the waveguide. If you apply a voltage across this PN junction, and let's just assume that you're just applying a reverse bias voltage, that means that your depletion region is gonna get bigger and bigger. And as you make your depletion region bigger and bigger, you are removing charge from the center of this waveguide. Now, when you have free carriers in a waveguide, those carriers alter the optical properties of the waveguide. And because of the excess free carrier, the waveguide becomes more lossy and the effective index changes, which changes the amount of phase variation as light propagates through it. When you apply a voltage and take the carriers out of the center of the waveguide incurs less optical loss, and also the effective index changes. So the amount of phase shift that you see as light goes through it changes. And so that's how you can change the optical property of the waveguide by applying a voltage across it. And that's possible because you have formed a PN junction here to start with. So that's one key mechanism that we use to create these phase shift key components in defining a lot of building blocks in active photonics. Whether you're using a ring modulator or you're using a Mach-Zehnder type modulator, the building block are these basic phase shifters. And so that's why we created this waveguide and we doped it with PN doping, and then we have this contact so that we can apply a voltage. So the next step would be to apply those voltages. So we're going to add some boundary conditions. And so we are just going to add 2 electrical boundary conditions, one for the anode contact, one for the cathode. And then let's edit one at a time. So we are doing a steady state simulation. So we can keep these to steady state. And then on the anode, we can apply, we can make this our ground. So let's keep this at single and then we set it to 0. Now we are not going to use this part here, but you can see that when you're doing an electrical simulation in charge, if you have, let's say, contact resistances or shunt resistances outside your device, you can actually enable these and then add them when you run your simulation. So this is one way that you can include effects of contact resistances and such non-idealities in your simulation. So for this particular example, we're just going to keep them disabled. And then for cathode, and then the other thing that we have to do is we have to assign this anode to one of the contacts. So that's done in the geometry. And then what we can do is where do we want to apply it? So we want to apply it to the surface of a solid. So I'll select the solid option here. And then that particular solid would be the anode. So when you select solid, this drop-down menu shows you all the geometries that you have in your objects tree. So we are just kind of seeing this list here, and then we can select the anode rectangle from this list. And as soon as you selected anode, you can see that the surface of the anode gets highlighted. So this boundary condition is actually getting applied to the surface of the anode geometry. And that becomes evident here. So similarly, we'll pick the cathode boundary condition. Again, it's a steady state simulation, but this time around on cathode, we are going to apply a voltage sweep. So let's choose the range option. We're going to start from 0 to, let's say, 4 volts. And then maybe we'll have 11 points to do the sweep. And then in terms of geometry, again, we select solid, and then we select cathode. And then you can see this one is highlighted. So just to show you that the boundary condition can be defined in different ways, let's try one other thing. So we have these two domains for the two contacts, and domain 2 is actually the domain where our cathode is. So I can also go into cathode. In geometry, instead of selecting solid, I can actually select domain, and then I can actually select domain 2, which I know is my cathode domain. And if I say okay, you can see that my cathode is still applied to the region. So there are multiple ways in which you can apply a boundary condition to some surface or some solid. And so here you can see that we use the solid option to define anode, whereas we directly applied cathode to this particular domain. So again, like there are multiple ways of applying a boundary condition. And yes, so I think that's should be it. Our simulation has been set up. So now we can click on the check button to make sure that there are no warnings. And then if we, instead of clicking run, maybe first we just click on mesh. And then so that way our design is going to be meshed. And then in the chart solver, you can actually view the mesh now. So if you right click, visualize grid, and then that shows you the simulation mesh. And then if I zoom in here, you can see the simulation region. So positive value here, because we are looking at N. So this is positive value for the N-type doping and negative value for the P-type doping. These are high values. And then in the center, the shading is really similar, hard to identify, but we have N doping on this side and P doping on this side. You can also choose to plot signed log. So then you can now bit more clearly, you can see that you have side and P doping on the other side. Click anywhere and then W, then I can actually see the mesh. So you can see the triangular mesh. So you'll see that because I tried to make the mesh very coarse, so it actually looks really coarse. But as you can recall from the slide, that when you're running an actual simulation, a proper simulation, you usually make the mesh much finer than this. Yeah, actually, just to make sure that the result doesn't look very weird, I'll probably make this mesh a little bit finer. So maybe I'll make this 0.1 and then make this one 0.3 micron, maybe 0.5 micron. And then now if I calculate the mesh again, you'll see that since I made my mesh settings finer, I should end up with a somewhat finer mesh. And so I can view it again, zoom in and hit W. And then so you can see that the mesh is a little bit finer now. So we can just stick to this and then now do our bias sweep. So now I can hit run. And then since I set up the voltage in the cathode to go from 0 to 4 volts, you'll see that my simulation now sweeps to 0 to 4. It's done. And then the icon for the chart solver tells me that there are results here. And so now in the window, you can also see what are the results available. So you have information like mobility, recombination doping, and so on. And then you have results for anode and cathode. So these are the results at the two contacts. And this is where the current at the contacts are recorded. So you can either visualize the result directly from here, or you right click on the solver itself and then select the result that you want to see. So let's look at the current at anode. So we click on this. And since it's a reverse bias diode, so the current is going negative. There are multiple results because it allows you to look at current due to holes, due to electrons. I've removed all of them. And so this is just the current due, like the total current in my anode. And it's negative because we are going further into reverse bias. The other thing that we may want to look at is the charge density profile. So if we look at charge, the same result shows you the charge density as well as the current density, so Jn and Jp, but we are more interested in the free charge or the N and P values. So let's look at the N density. We probably should just look at the signed log. And then as I change the bias sweep, I want to log the camera so that the zoom, I don't lose the zoom. And then here in the parameter window, you can see my voltage applied. So if I click on cathode, you'll see the slider appears because this is something that we're sweeping. And then now as we change the bias, you see that the density is reducing in the center because it's going into further into reverse bias. And so the charge density in the center of the waveguide is going down. And so as I go further and further into reverse bias, you can see I'm depleting the charge here and the density is going down. So you'll see the same thing for holes. So at highest bias, the center is getting depleted of holes. But as I go back to 0, I can see that I go back to my initial doping profile where I had like lots of holes in the center as well. So when you're doing a multi-physics simulation, say for a phase shifter, this is the result that you want to save from a charge simulation, like the density profile. And then once you have the density profile saved, you can bring it into mode, like in Fde, and then you can run a simulation where you can change the refractive index of the silicon waveguide as a function of this charge density. And so then when you calculate the effective index of the waveguide, you will see that as you change the voltage and as you change the charge profile, the behavior of your optical waveguide is changing. And then that allows you to model the behavior of the electrical phase shifter. So in order to do that, what you would do is you would actually use a charge monitor. So now we have our simulation setup done, but we haven't used any monitor so far. So let's place a charge monitor here. And then in the monitor, you can either define it to have a 3D geometry. And then in terms of geometry, you can define the extent so that it just covers my entire silicon waveguide. So I'll make the X span, I'll just make it big enough so that it covers everything. My monitor can actually be a 2D monitor because I'm running a 2D simulation. So it can be 2D Y normal. And then that way I don't have a Y span to define. But then my Z span would be, again, I'll just make it big enough. So it's a 0 to 1 micron. Now the monitor doesn't show up in the window because it only shows up, it's a simulation object that only shows up when you're in the partition volume. So if you click on partition, and then I select my monitor, then the yellow box shows me what is the area that I'm simulating. And just to show you where the silicon was, this is where the silicon was. So I'm actually covering the entire silicon. And if I go into the properties of the monitor, you'll see that there is an option to save the data. And you can save a file name. So I'll say charge density.mat. So then when the simulation runs, after the simulation finishes, the solver will record the density for that entire volume inside the monitor and then save it in a MATLAB file that you can load into your mode simulation. And just to show you, once I save this and then I run this, the charge density will be recorded into the monitor. So we can directly view it from here. So it's the same charge density on the waveguide. And then now if I go out of these, and I can see that there's a MATLAB file that got saved in the same folder. So this is a MATLAB file that you can now load into mode and then perform an optical simulation for the phase shifter. Okay, so hope that helped. In terms of other examples of using charge solver, let me just open up maybe a few more examples. So I'll open up the launcher here. Okay. Maybe I should show how you can get it. So if you do a new here or you do Control N, then the launcher comes up. And then if you go to examples, then it shows you the different application examples that are available. You can browse through them by typing charge here, then it'll show you the simulation files or the examples that are specific to charge. So one other example that we can look at is maybe a vertical photodetector. And so I'll just download this. Okay, I'll have to sign in. Okay, so it's downloaded. I'll just maybe download it on my desktop. And then once the example is downloaded, it automatically opens up. Like if it's a multi-physics simulation, then there could be like multiple solvers involved, and it opens up all the different files in the different solvers. So here you can see that it opened up charge here, but it also opened up FDTD because we are simulating a photodetector. And yeah, I guess like this example also shows you how you can simulate and optimize the photodetector in EME. But yeah, for the sake of today's discussion, we won't go into that details. So I'll just close this one for now. Let's see, which one is this one? Right. So I'll kind of like just quickly show you what would be the flow if you're trying to simulate a photodetector. So when you're simulating a photodetector, again, the first thing would be to do the optical simulation because you want to figure out how much of the light is getting absorbed in your photodetector. And then from that, you will know how much electron hole pair generation is going to happen in your electrical simulation. So we will start with the FDTD simulation first. Let me turn the mesh off so that you can actually see the geometry here. So this particular view, I believe, is useful. So you have your silicon slab here. It's a germanium photodetector that we're looking at. So you have your silicon slab here, which is your waveguide. So light comes through here. And then you have your germanium slab on top. As light comes in, and you have this germanium layer starting, light will couple into the germanium layer. And since this layer is absorbing to the light, light will get absorbed. And so you have contacts connected to the germanium and the silicon layer that are then used to collect that light. Let's see what other, and then, so if you look at the simulation setup, you'll see that in terms of geometry, we have the surrounding oxide, we have the silicon slab, we have like the waveguide portion at the beginning, and then we have the germanium layer on top. And then on top of germanium, we have this metallic cathode. In this particular simulation, we haven't included the anode because we are just focusing on the optical simulation. But as we go to the charge solver, you will see that we will include the anode there because for the electrical simulation, you of course need to include the electrical contacts. What's more important here are, like, for example, the sources. So here you have the FDTD simulation region. It's a 3D simulation because it's a 3D photodetector. So maybe I'll open this one up. So this is the cross section of the photodetector. If you look carefully, again, this is the silicon slab, and then that's the germanium layer on top, and then that's the contact at the top. And light is going into the monitor here, into the photodetector. In terms of source, so FDTD is a 3D solver here, as I mentioned. And in terms of source, we are using a mode source. So you have your waveguide and you inject a mode source, light using a mode source into the waveguide. So the fundamental mode that's supported in the waveguide, that gets injected, and that kind of like replicates the actual scenario that you would have in your actual photonic circuit. light would come through a waveguide and then couple through a taper into the silicon slab as well as the germanium region. So it's all getting simulated together. And then what's important to notice here is that when you have a simulation where you want to capture the optical absorption and you want to figure out the electron hole pair generation, you use this generation rate analysis group. So this generation rate analysis group allows you to calculate the electron hole pair generation from optical absorption. And wherever you want to calculate this generation rate, you put this generation rate analysis group on top of that layer. So that's why you see that this yellow box here. Let me make this bigger. So this generation rate analysis group has this volume, and it is covering the germanium slab because that's where the absorption and electron hole pair generation will take place. And this analysis group is available in the object library. So it's already built in. You don't have to create it manually. So if I open up the object library here, you see that in the object library, you have two categories, two types, structure and analysis. So the structure group contains different types of geometries, complex geometries that are readily available and you don't have to create them manually. And then in the analysis section, there are like lots of different analysis tools that you can also use kind of like off the shelf. You don't have to do those calculations manually. And then so inside optoelectronics, you have the CW generation rate and the solar generation rate. So the CW generation rate is what you use when you're modeling something like a photodetector, whereas the solar generation rate is exactly similar as to the CW generation rate, but it's for solar illumination. So that is something that you would use when you're doing a solar cell simulation. So here, this generation rate object is actually this CW generation rate analysis group. Now, if I go into this property, you'll see that it has some predefined variables. And so the more important parameters here are the X, Y, and Z span. So that kind of like defines the volume where you want to do the calculation. And you don't really have to do anything else here. The script itself sets up the necessary index monitor and electric field monitor that it uses to do the final absorption calculation. And then again, in the analysis section, you can select the file name where the generation rate is going to get saved. And so when you run the simulation and do the analysis, it'll save the generation rate in a MATLAB file. You can define the name. And then in charge simulation, you'll see that you can simply load up this file, and then the generation rate will get imported from FDTD into charge. This number of period input is something that you can use when you have a uniform simulation region that you're going to just simulate a small portion of the device, and then you're simply going to copy that information over and over again just to make things more efficient. So then you can use like multiple number for this period, and then you simulate one slice of your volume, but then you can extend it by a factor of any number that you put here to create a bigger generation rate that you can include in charge simulation. In some cases, you do a 3D simulation in FDTD, but then when you're doing the charge simulation, you can choose to run a 2D simulation there. And you can do that by averaging the generation rate in one particular dimension. And that's something actually that we are doing here. So even though our FDTD simulation is 3D, when we do the charge simulation, we actually do that in the cross section. And then we have like one contact here and another contact on the silicon slab, like anode and cathode. And then we simply do a 2D simulation in charge just to make things more efficient. And so that's why what we do here is once we calculate the generation rate, we average the generation in the X direction, which is the optical propagation direction. And that's defined here. And then so the final generation rate that gets saved, the generation rate kind of like gets averaged in the X direction. And when you do your charge simulation on a cross section, you can simply make the length in the third dimension equal to the length of this entire germanium. And then the current that you will end up in your charge simulation will be close to the actual photocurrent that you get from this detector. So that's where kind of like the norm length that we saw in charge simulation comes into play. And then the source intensity would be simply the intensity of the optical signal that goes in. So you can simply set that to 1 watt, or in terms of intensity, it would be like 1 watt divided by the surface area of your simulation volume. And then that way you get like a normalized absorption in your simulation. And then you can see the outputs that you get out of this analysis group are the PABs and PABs total. So the absorption spectrum and the total absorbed power, JSC, which is a calculation of the photocurrent. So this is the maximum photocurrent that you can get from this photodiode, assuming that none of the photo-generated carriers are getting lost. So that's kind of like the maximum current that you can get. And then G would be the density of the photo-generated electron hole pairs. So this is the main number that gets saved in that MATLAB file and then get exported to charge. And so when I run this simulation, it'll light will simply go through, get absorbed, and then you do analysis, and then the generation rate gets saved. And then now if we go to charge, you can see we have the entire photo detector here, again, like a 3D volume. But looking at that orange rectangle, you can see that we are actually going to run a 2D simulation. So I'll just look at a side view here. And so you can see that that's the cross section. So this is the silicon slab, and then the germanium layer on top. And then we have the 2 metal contacts for our anode and cathode. And now in this particular simulation, you can see that the photodiode is actually symmetric. So that's why we are running the simulation on half the cross section even here. We are not simulating the entire cross section. And that's because we are assuming that it's symmetric. So let's just run simulation on 1/2. Again, in terms of simulation setup, we have our materials: aluminum for contacts, silicon for the slab, germanium for the absorption layer, and then oxide for everything else. And then again, geometry, we have these different blocks that combined create our complete device. Simulation region, 2D rectangle. And then if we go into the charge simulation object, you see that this gen object is actually the optical generation rate object. It's disabled for now, but we will enable it. And then we have our doping profile. So if I switch to partition volume, you can see that that's what we're simulating, like half the cross section of the photodiode. You can see the different domains. And then the doping objects. So we have a constant p-type doping on the silicon slab. Some of that p-type doping gets diffused in the germanium. So that's getting defined by this p- diffusion doping object. And then you have this N++ doping to dope the contact on your cathode up here. In terms of boundary conditions, we have 2 electrical boundary conditions on my anode and my cathode. And then we have some surface recombinations to calculate the surface recombination at the different material interfaces. So because this is a photo detector, it's important to model these surface recombinations, because often as you generate the electron hole pairs, they recombine at these recombination locations at the interfaces. And that is a key source of loss in photocurrent in this type of devices. So it's important to use these surface recombination boundary conditions and then include them in your simulation effects. So with everything set up here, we can run one simulation with the generation rate disabled. And so that will give us the dark current of our photodiode. So let's see if this runs fairly quickly or not. Okay. Yeah, I guess like for an app gallery example, it probably has a finer mesh. So let's skip this for now. We have quite a few other materials to cover. So I'll just quit this for now. But hopefully that shows you kind of like the complete flow. You'd first run the optical simulation, get the generation rate into charge. So maybe I'll just quickly show this generation rate object here. So if you open this one up, it's nothing fancy. The main point here is the data part. And then so you can see that you can import the file here. So you simply browse, and then you pick the generation rate.mat file. You open it up, and then it shows you the data that's coming from FDTD. And you can choose to use a scale factor if you want to. So remember that when we defined the optical generation rate in FDTD, we defined a source intensity. If in your charge simulation, you want to change the optical power and want to see how the photocurrent varies as a function of that, you can now scale the generation rate here as well. And then that way you can scale the total generation rate for a certain optical power, and then use that in your electrical simulation. And then you simply select the attribute G here, because that's the generation rate data. And that's it. So you simply load the data, you click OK, and then the generation rate comes in. If I enable it, and then I click partition, and then I select the generation rate, it kind of like shows you the extent of the generation rate data. So you can identify that this was kind of like the extent of the germanium layer in my FDTD simulation. And so that's where the data is getting, that's the volume over which the data is getting imported. So that was the length of the photodetector. So that's the 3D generation rate that we are importing. And it automatically then gets included in your electrical simulation as you run it. Okay, let's close this here. Okay, so now we're going into heat. So heat, as I mentioned, is the thermal solver. So the main purpose of heat is to allow you to simulate thermal or heat transport through solids. So it only models heat transport through solids. If you have, say, air surrounding your device, which would be the case in most situations, or you have maybe some cooling liquids surrounding your device, you can still account for them by applying boundary conditions. So most importantly, like convection boundary conditions, you can apply them to the boundary of your device, and then that way, if heat is escaping your system by convection through the air or by some fluid, you can still account for that. However, the actual simulation always takes place within solids. This is also a solver based on finite element mesh. It can perform steady state and transient simulations. And then it has the usual boundary conditions required for thermal simulation. So you can define uniform temperature on different surfaces. You can introduce a thermal power coming in from any of the boundaries or a heat flux. And then of course you can define convection and radiative boundary conditions on the surfaces. And then the results that you usually get out of these simulations are the temperature profile. And if they're power generated or power absorbed in the system, then you can also get information about that. Some of the applications would be, for example, thermal waveguides. So devices like ring modulators or Mach-Zehnder modulators, you often use thermal heaters to tune their behavior. And so that's something that you can model using heat. Of course, combined with an optical solver like FDE. Thermal switches, so an extension of the waveguide tuning by definition. Also maybe for plasmonic heating. So this is an example of a Diabolo antenna where you have a metallic antenna on top of a semiconductor, and then you shine light on the antenna. The metal absorbs the light and gets heated up. And then if you want to see the temperature profile of the whole system, then you can bring that absorbed power information into heat, run a thermal simulation, and then that shows you what would be the temperature of this antenna as it absorbs light. In terms of solver physics, it's a much simpler solver compared to the charge solver. You simply solve a single equation for the heat transport that covers both steady state transport and transient transport. And then like the heat solver also supports Joule heating according to Ohm's law. So it actually has a simple conductive solver inside it where you can define the electrical conductivity for every single material in your system. And then if you apply a voltage to your system, it will calculate the current flowing through it by using Ohm's law. So current density equals to �sigma.E. And then based on that, it can calculate how much current is going to flow in your device. And then that can give you the Joule heating that happens. So if you have a simple metal heater on top of your waveguide and you want to see how that heater is going to heat up your waveguide, you can use this simple conductive model to figure out how much current is going to flow in the metal heater, and then do a thermal simulation to figure out what would be the temperature on your waveguide as you're tuning it. So that's a pretty useful tool to have in this solver. In terms of material models, again, the most important material model are for solids. And then you can define different thermal properties. So the thermal conductivity, density, specific heat, and also if you're using the simple conductive model to calculate Joule heating, then you have to define the electrical conductivity of the materials as well. The thermal models also support nonlinear behaviors. So for example, thermal conductivity can be a function of temperature. In terms of boundary conditions, the most common one is a fixed temperature boundary condition. So for example, if the bottom of your device is at room temperature, like acting as a heat sink, you just define a fixed temperature boundary condition there. If there is heating happening on one of the surfaces, you can define a power boundary condition or a heat flux boundary condition there. Convection boundary condition to model heat loss from the top surface, that air, if you have air surrounding your device and that's taking the heat away from it, you can define a convective boundary condition. Of course, like you can have radiative boundary condition to model heat loss from radiation. And again, if you want to model Joule heating, you can also define voltage boundary conditions. And then that way you can, when you apply a voltage to your system, using that electrical conductivity of each model, the solver can calculate the current flowing through it, and then that way model Joule heating. So this is a tab for the heat solver. Again, you have the mesh constraint for like refining the mesh, and then different boundary conditions, sources. So here, like you can import a heat source into your system and see the effect. In terms of monitors, you can either see use the power flow monitor to calculate the heat flux flowing through any cross section of your simulation, and then the temperature monitor to get the temperature map. And on the final part, like these are very similar. You can partition the simulation volume, calculate the mesh, and run the simulation. So there are like some simple examples that we can take a look at. So I'll maybe just close the slides here, open up heat now. And then I'll open up a simple heat example. Yes. Okay. Guess can't see a simple enough simulation, so I'll just look at the solar cell example, which is pretty interesting. So let me just download this. So this is an example of a simple solar cell. However, this example kind of like shows you the different aspects that you can consider when simulating a solar cell. So it's actually quite interesting. So if we go through the simulation flow here step by step, and then we will end up with heat at the end. But first, if we look at the Fdt simulation, it's a simple simulation setup. So we have our silicon silicon absorbing layer, and then we have metal contact at the bottom, which is the base here. Light is coming through the top, so it's a plane wave source. And since it's a uniform geometry, we made the simulation volume like really thin, just because like it's gonna be uniform everywhere. And then now you can see that we have used the solar generation analysis group. So last time we were using the CW generation analysis group. This time around, we're using the solar generation analysis group because it's a solar cell. And then so you simply run the simulation, light goes through the silicon slab, gets absorbed, and then the analysis group calculates how much electron hole pair is getting generated inside silicon. And then the next step, you go to the charge or heat, so the finite element design environment. And then here you import the generation rate into charge. So again, you have the materials defined, you have the geometries defined. Let me just turn it. So that's how the silicon solar cell looks like. So again, this is my silicon. That's the bottom metal contact, and then that's the top metal contact. So these form my anode and cathode, and then my active region here. I have some doping here. So if I go to my partition volume, you can see I have a constant background doping. I have a P++ doping on the back surface connecting to the bottom anode, and then an N++ doping at the top connecting to the cathode. And then the optical generation rate. So this blue line here shows you that the generation rate got imported from FDTD. And then I have some monitors to calculate the charge and so on. Now, when we run this particular simulation, one effect that we are trying to capture here is when the solar cell absorbs the light from the sun, the absorbed power from each of the photons get used up in two different ways. So one is you generate an electron hole pair. And so that means that whatever the band gap of your silicon layer is, you require that much energy from the photon to create that electron hole pair. However, within the solar spectrum, you absorb a lot of photons that have energy much higher than the band gap of silicon. And so when you absorb these photons and then they generate an electron hole pair, only part of the energy of the photon is used up in creating that electron hole pair. And then the rest of the energy is getting used up as thermal energy. So what we have done in this example is we have calculated how much of those, how much energy of those photons are getting absorbed to generate electron hole pairs. And then we have kept track of the extra energy from those photons that are getting converted into thermal energy. And so in this heat source object here, we actually imported the generation rate data from, sorry, let me go back to FDTD here again quickly. So we actually calculated the absorption power from the solar generation rate. So if you go to the analysis, you will see that we have modified this analysis group a little. So it exports the G, which is the generation rate, but it also exports the thermal absorbed power. So that means that we have adjusted the analysis script here slightly. And then so for the photons who has energies above band gap, we calculated how much energy does that photon have above the silicon band gap. And then we have converted that into a thermal power that we can bring into the heat simulation to figure out like how the solar cell would heat up. And so that when we run this analysis group, it actually saves 2 data files, or I believe a single data file that contains both the generation rate and the thermal power. And so now in the heat simulation, we have this heat source. And then on that one, when we loaded the data, this Pabs thermal is the amount of energy that is getting converted into heat into the solar cell. And so first, we run a heat simulation to figure out how much the temperature of the solar cell will be elevated as it operates and absorbs sunlight. And then in terms of boundary conditions, we assumed that it has just air on top and bottom. And so it's just convection that's taking heat away from the solar cell. So we just have like two boundary conditions on the top surface, from the top surface of the silicon, and convection from the top surface of the oxide. And we have the heat source heating up the bulk of the silicon due to absorption. And then we have a temperature monitor surrounding the entire geometry. So once we run the thermal simulation, it'll capture the temperature map, which we will then include in our electrical simulation. So let's just run the simulation here. So that's the thermal simulation run. And so once the simulation is run, you can see that the heat solver now has results. And so if we right click it and look at the thermal option, then it has the Q. If you're getting any heat generated, then Q shows that. But more importantly, if you click on T, then that shows the temperature map. And so you can see that even though the color map shows some gradient, that's just because of numerical differences in the data. You see some variations, but actually you can see that entire solar cell is at an elevated temperature of 320 Kelvin. So as it's absorbing sunlight and producing electron hole pairs, it's also getting heated up, and the temperature has risen by 20 degrees here. So now when you perform the electrical simulation of this device, you need to account for the fact that the temperature is not 300, but 320. And so the way we do that is when we set up our chart simulations, you'll go to the editor, and then you can see that in terms of temperature dependence, instead of using an isothermal, we will actually use a non-isothermal mode. And so when we select the non-isothermal option, this temperature or heat source comes into effect. And so then in this particular object, we can load the temperature map that was captured by this heat solver. So we've already loaded the data and then selected the T attribute, which is the temperature data. And so if you just calculate the mesh, then you will see whether the temperature map is actually getting imported. So I'll just calculate the mesh, and then I'll look at the grid. And then so you will see that that's the optical generation rate that's coming into the system. If I do a log scale, it becomes more evident. So that's the optical generation rate coming into my simulation volume. That's the 𝐺𝑜PT external. Okay, I don't think the temperature map shows right now. So if I run a simulation now in the chart solver, then we will see that it actually captures the temperature variations as well. Let me just make sure that all the results are set. So yes, so in the results tab of the chart solver, you can actually select what results you want to capture and what results you don't want to capture. So as long as the thermal mode is enabled, then it'll record the temperature in my electrical simulation as well. So I'll try to run this quickly and then see if this runs. fast enough. Okay, so it was a single bias voltage simulation. So now if I right click and visualize thermal, then you can see that in terms of the temperature, my entire silicon region is actually at 320 degrees. Is at elevated temperature because I imported the temperature map from my heat simulation. And so that means that the carrier properties, the material properties in charge, they are temperature dependent. For example, the recombination rate is a function of temperature, the band gap, mobility, they are all function of temperature. So since the device is at an elevated temperature, it'll behave in a different way. And then this allows you to capture that. Okay, so let's take a look at interconnect now. Yep.
Dr.
Any
Alom,
question?
I have a question. As we know that, as you already mentioned, that the band structure is a function of temperature. So is the band structure automatically updated with the elevated temperature in the simulator, the charge simulator?
The voice question. Can you repeat, please?
Of course, extremely sorry about that. But what I was asking that the band structure is a function of temperature. So is the band diagrams and band gaps are automatically updated with the elevated temperature in the silicon structure?
Yeah, the voice is still breaking up for me. It might.
Could you kindly please write it in the chat, then I may read it out.
Why type?
Hello, SM 𝗕𝗓𝗓𝗓𝗓, could you kindly type it?
I can.
But actually, he asked another question before. You can also answer to that question.
Exotic materials in simulation. So the most cases or for most too, right? In those type of you see quantum effects come. The uses a semi-classical approach to simulate the electrical transport. Yeah, the simulation to the material is actually you actually don't have like 2D electron gas, right? You have a 1D band profile, and so the nature is quite different from what you have in a 3D crystalline material like silicon and germanium. Like the band profile is quite different, and so just like the nature of the band diagram or the 𝐂𝐄𝐄 diagram for your materials is going to be quite different, and the model, even if you use some like fitted effective mass to define the behavior, it just won't be very accurate. Okay, so thanks for typing in the question. I can see that the question was, is the band gap automatically updated when temperature changes? And the answer is yes. So if you go into the charge solver, and then if you look at the material database, you'll see that for a lot of the properties like recombination rates and as well as like band gap, you have different models associated to them that allows you to vary them as a function of temperature. And then so in that case, if your simulation temperature changes, those properties change as well. Okay, so let's go into interconnect now and talk about circuit simulation a little bit. So as I mentioned, interconnect is our photonic circuit simulator. So so far, all the solvers that we talked about are component level solvers, right? So you simulate individual elements, you look at the physics behind their behavior, and you simulate them individually and figure out how they behave. Interconnect comes into play when you have a big system, which has lots of parts. And so it doesn't make sense to simulate that big system at a very fundamental level, right? Like by solving Maxwell's equation or diffusion equation for a huge system is computationally very inefficient or even impossible. And then in those cases, you actually create compact models for all the different pieces, hook them up as a circuit, and then you do a circuit simulation. Just like you do circuit simulation for electronic systems, you can do circuit level simulations for photonic circuits. And so that's where interconnect comes in. So interconnect is, I guess, most widely used in silicon photonics, just because I guess in terms of photonic integrated circuit, that's the most matured field right now. But the same concept applies for any other photonic circuits as well. So if you have 3.5 based or silicon nitride based circuits, you can use interconnect to simulate those as well. So you can bring your building blocks into the interconnect schematic editor, hook them up, bring in your sources like lasers and photo detectors for detection, and then run a simulation of the full circuit. Interconnect allows you to perform both time domain simulation and frequency domain simulation. So you can frequency domain simulations are usually much simpler and can be run quickly to just figure out the idealistic behavior of your system. And then you can do time domain simulations, which usually are more time consuming and complex, but it also allows you to perform signal integrity for your system. So get more important information about the performance of your system. So here are some of the key features of interconnect. So it's a circuit solver, so it uses a hierarchical schematic editor. So you can create your circuit and you can have different levels. So you can define, for a huge circuit, like you can break it down into different compound blocks and then go inside the blocks and then define sub-circuits. So that way you can keep hierarchy in your design and keep things cleaner. It comes with an element library that contains a lot of the common passive and active building blocks. So simple waveguides, photo detectors, modulators, they all come built in with the interconnect object library that you can simply drag and drop into your schematic and start building your circuit. It also comes with different types of optical sources and measurement elements or analyzers. In terms of circuit solver, as I mentioned, it comes with time and frequency domain analysis. The optical signal propagation in interconnect is fully bidirectional, and it also supports multi-mode and multi-channel support. So you can if your device supports both T and TM modes, like you can just run a single simulation to see how they propagate through your system, as well as multi-channel simulation is done in a single run. And then it also has a SPICE interface, so you can hook it up with external electrical solvers like Spectre, and then run electro-optical co-simulation. In terms of visualization and data analysis, it has an optimization workflow similar to the component level tools. So you can optimize your circuit using that or run parameter sweep. And then on top of that, it can perform statistical analysis and perform like statistical analysis like Monte Carlo sweeps. So the statistical analysis part is pretty critical when you're doing a circuit simulation, just because When you're going into circuit simulation, then you have so many components in your design, and as you fabricate them, you can imagine that there's always some variation coming from the fabrication process. So what you originally aimed to be the performance of each individual blocks, when you fabricate them, usually they all behave in slightly different way. And so when you're doing your design and you're running your circuit simulation, you want to make sure that even if those slight variations are happening, whether the entire circuit is gonna be performing according to spec or not. And that's something that Monte Carlo analysis allows you to do. So when you run your simulation, the solver will randomly change the behavior of each of the building blocks, and then run multiple simulations, and then at the end give you a report as to say what percentage of the devices, what percentage of the circuits that you ran simulation for are performing according to spec, and that way you can get the yield of your circuit in the end. So this is kind of like what I was mentioning, that when you're running simulations for a photonic circuit, often you have active devices in there, and in order to bias the active devices, you need electrical drivers. So in many cases, you want to actually run an electro-optical circuit simulation where you want to model the drivers driving your photonic circuit simulated in an electrical solver, like a SPICE solver, either in Cadence or Mentor Tanner. And then you want to run the photonic simulation in interconnect, and there are interoperability options available that allows you to do that. And then interconnect also allows you to create compact models for your individual photonic elements. So for example, the phase shifter example that we just saw, you would start at the component level, you design your device, and you run electrical and optical simulation that tells you how the phase shifter behaves. But then that phase shifter could be part of a bigger circuit. And so in interconnect, you can actually create a compact model for the phase shifter, and then use that in a big circuit simulation. For frequency domain simulation, interconnect defines every single element by using their S parameters. And then that way you can calculate a combined S parameter for your whole system and perform its frequency domain behavior, figure out the frequency domain behavior. And the way you do this is by using the optical network analyzer. So you can connect the optical network analyzer to your circuit. It acts as the source, and then at the same time, it acts as the visualizer. So you hook up all the outputs to the analyzer, and then if you then run a simulation, the analyzer calculates the S parameter of the whole system and gives you the frequency response. So here it also shows you the hierarchical definition that the interconnect supports. So here, for example, you have a ring resonator, and this can be a compound, and inside the compound you can have a ring defined. So here you can see like a waveguide coupler on the top and bottom. So you have a like the two optical bus at the top and bottom, and then you have the ring inside. The couplers couple the ring with the top and bottom bus. And then you have like the waveguides inside to create the ring. And so that's kind of like these four components create a single ring resonator. And then so you use a compound that includes this everything inside it. And then on the top level, like you can simply have these compounds build your entire circuit. And the output would be, say, the frequency spectrum for your device. Again, in time domain simulation, interconnect calculates the transient analysis of, well, transient response for each of the individual elements, and then performs time domain simulation. And so this allows you to perform integrity analysis for your signal, for example, in actual cases. So things like eye diagrams for your receiver, that, for example, something that you can get out of a time domain simulation, which you cannot get from a frequency domain simulation. And then one other thing to mention here is that when you run either a frequency or a time domain simulation, interconnect supports optical signal propagation, of course, but it also has support for electrical signals as well, so that if you have active elements in your design, you can bias them. Of course, given that the main focus of interconnect is optical simulation, the electrical sources that you have are pretty primitive and idealized in most cases. So ideal DC sources or ideal pulse trains, those are available, and then you can hook them up with your optical devices to bias them and run simulations. So this is the interconnect user interface. Again, there are some things that are similar to the other tools, but because it's a schematic based editor, so things are a little bit different as well. So first thing is that like the center here is not a CAD window, but it's a schematic where you create your circuit and hook them up with each other. And then you have the element library. So this is where you have all the readily available photonic components. So like the sources, the waveguides, amplifiers, and so on, all available here. And then you can drag and drop them into your schematic. The elementary down here kind of like shows you a hierarchical representation of all the different elements that you have in your circuit. So if you have compounds and like sub-circuits, you can expand the list here and see what's in there. The property editor shows you the property of each of the individual elements. So as you select the waveguide or you select the coupler, like you'll see the parameters for them showing up here. And then the port list kind of like shows you the different ports. The run button allows you to run the simulation here. And then the output window is also something unique to interconnect. So as you run a simulation, the output window kind of like shows you the kind of like the log as your simulation runs. And then if there are any errors or warnings, that also show up here. So you can see right away if if everything is going on fine or if there are some warnings or errors. And then finally, the result window. So if you select any of the analyzers, then the result window shows you what are the results that are available after the simulation has been run. You can right click on any of the results and then visualize them, and then they open up in a visualizer window. The script prompt is very similar to the other ones. So all of the tools, including interconnect, supports a Lumerical scripting language. And so you can set up your circuit using scripts, you can run analysis using scripts, and so on. Similarly, script editor allows you to load a script file and run them. And then the optimization and sweep window, it's similar to the other tools. So you can run parameter sweep, you can do optimization, and then of course you can also do statistical simulation like Monte Carlo sweeps. So when you're creating a circuit and running a simulation in interconnect, the typical workflow would be you'd first add all your circuit elements. So either from the primitives, or in a lot of cases, like if you're actually creating a circuit that you want to fabricate at a foundry, then you can get a compact model library from the foundry that you can install in interconnect. And then so that way you will have all the components that the foundry offers available in the interconnect element library as well. So you can drag and drop a waveguide that the foundry offers as part of their process, or a Y splitter that's part of their process, and then add them to your schematic to build your circuit. So for example, like you'll drag and drop everything in the window, and then you'll hook them up by connecting them. And then you add analyzer elements. So for example, like the optical network analyzer to perform some frequency domain simulation. So it acts as a source. So light goes into, say, this coupler, and then for all of your outputs kind of like go into the analyzer so that you can visualize them. Set the properties of each of the elements. So say set the properties of the waveguide, the effective index, group index, and so on, the coupling coefficients for the coupler, update those values according to your needs, and then you run the simulation. And then once simulation is run, you can visualize the results from the analyzer. So now here are like some of the elements that are readily available in interconnect. So for example, one obvious thing to look for would be the waveguide. So if you go to the element library in interconnect, you see a detailed list of what's available by default. If you click on the waveguide, you'll see like lots of different types of waveguides available. And so you can select any of the waveguides, drag and drop them into your simulation and use them. There are like also two specialized components that you can use. One is a scripted element. So if you use a scripted element, you can actually define the behavior of that element using Lumerical script. So if you open up the property editor for a scripted element, you'll see that it has setup scripts. And then so you can write a script to define the behavior of your device, that if X input comes in, output would be Y, and so on. So you can manually define that behavior and then use that to model practically anything if it is not available in the primitive library already. And then the other one specialized element is the compound element. So a compound element is something that you use to create hierarchy in your design. So with the compound element, you can create subcircuits and add multiple levels to your design. So for example, like you can have a compound element and then a subcircuit inside it. So once you drag and drop one of these primitives here, like it'll have like some properties that come by default, but then it'll be up to the user to define those parameters appropriately, either from measurements, from experiments, or by simulation. So for example, when you drag and drop a waveguide, the behavior of the waveguide is defined by the effective index, the group index, and the dispersion of the waveguide and the loss. And so you can either run simulations in FDE, like we saw the other day, and then that tells you what is the effective index and group index, and then you just update the values. Or maybe you did some measurements on your waveguide and the values will come from there. So another option that you have in interconnect is you can either define the value of a property directly, or you can actually use expressions. So that can come in very handy. So for example, here length is defined by dividing the speed of light by, I believe, the group index of the waveguide. And I guess if you know how much time it needed the light to propagate through the length of the waveguide, like you put that number here, and then you can figure out what would be the length of the waveguide. So just an example that like you can actually parameterize the different properties this way. So you have an expression column where you can write expressions, and you can also use like common constants that are available in a scripting language. And then for every element that is in the primitive library, you can actually right click on them and click on help. This actually opens up the help page on your browser. And then that way you can get some information about the different properties of that element, like what it means, what are the default values and the supported range and so on. Okay, so I guess now we're talking about the analyzers that we use. So the most common analyzer that you will use in an interconnect simulation is the optical network analyzer. And the primary use of this is when you're doing frequency domain simulations. You simply use the analyzer both as source and as the output collect the output from your system. Okay, so I guess we're just showing that once you created your circuit, connect your analyzer to it, you supply the source to your device, and then you collect the output, and then you run. And then once the simulation is run, you get some output or some log message in your output window. And then once everything is done, then you have these results available in the analyzer, and then you can visualize those results. So you simply right click on any of the results, click visualize, and then the spectrum from the frequency domain simulation shows up. Okay, so some of the application examples of interconnect. So what type of simulations would you run using interconnect? So simply speaking, photonic circuits, right? So one example would be a wavelength division multiplexer, a transmitter maybe. So here is a block diagram or a cartoon kind of like showing the concept of wavelength division multiplexing. So what wavelength division multiplexing allows you to do is using a single channel, say a single fiber optical fiber, you can transport data, like a lot of data. And the way you do it is that if you have like multiple data that you want to transfer through that single channel, you simply modulate them at different optical wavelengths, right? So if you have like say 3 sets of data, you modulate them at different wavelengths. And so that's where the wavelength division multiplexing comes in. So here, for example, you have multiple channels. In one option would be that the signal propagates on a waveguide, and then you connect 3 different ring resonators in series with that, each of them tuned for a particular wavelength. And then you apply a modulating signal to each of those modulators to encode your electrical signal on top of the different optical signals, one wavelength at a time. So for channel 1, you're encoding your signal on a particular wavelength. Channel 2, again, you encode your signal on a separate wavelength, and so on. So once your transmitter, like all the optical signal goes through all the different modulators, you have information encoded on different wavelengths, and then you just transmit it over a particular channel and receive it on the other side. The same thing can be done by first applying different signals to different modulators and then hooking them up with the optical bus, and then kind of like accumulating them as you propagate through the bus as well. But the basic concept is the same, is that you use some sort of modulator that is tuned to a particular wavelength, and then when you apply an electrical signal on that modulator, it encodes that electrical signal into light. And then that way you can transfer it using, say, an optical fiber over long distances. And this is something that you would simulate in interconnect. So maybe I can open an example quickly just to show. So I'm opening up the launcher, Control N, go into examples, and then I'll do WWDM. So that's a more complicated examples than maybe I want to show. So I'll just go here. Okay, so I think that's a more suitable example. So this is an example that shows wavelength division multiplexing. So maybe I'll first open up a single channel one, and then we go to a more complicated circuit. Okay. So here we have a single channel wavelength division multiplexing transmitter and receiver. So this particular ring resonator, the way it works is that it has 2 optical bus. So light goes through a straight waveguide, and then there is a ring coupled to that waveguide. And as light goes through that waveguide, the only light of a certain frequency couples to that ring. Otherwise, light simply goes through. Now, when you apply an electrical voltage to this ring, the frequency at which light couples to the ring from that straight waveguide can change, because you're changing the effective index of the ring. And so hence, the resonant wavelength changes. And this is how you actually can modulate the behavior of the light that goes through it. Like, so we apply the electrical information as a pulse train, and use that pulse train to change the modulation of this ring here. And then that way, the light that goes through the bus here, we can change the amplitude of that signal according to the pulse train that's coming through here. So what the output that you get is actually gonna be a modulated version of the light that comes in, and the modulation will have these pulse train information encoded in it. Now that light goes through, let's say, a channel, optical fiber or something like that, and goes through the other end. So now you have your receiver. Your receiver is nothing but a ring which is tuned at the same wavelength as this original ring modulator. And so that way it can filter out the electrical signal that is encoded on top of the light at that particular wavelength. And then from the output of this ring, you can send that signal to a photodetector, which converts then the amplitude modulated light into electrical signal. And on the output, you finally get the original pulse stream that you applied to your modulator back. So now if we run a simulation for such a system, you can see that there are quite a few pieces here. We have a modulator, we have a ring resonator, we have a photodetector. And so it will be quite difficult to simulate these using the component level solvers. Whereas in system level, running a circuit simulation is quite easy. So now as the simulation finished, we can use these analyzers to look at different results at different locations. So we have the laser source coming into the ring, and this is our electrical signal that is modulating the light here in the ring. So maybe we can first take a look at the pulse train and how it looks like. Oops, what is it? So when I visualize the signal, so this is the electrical signal that's coming. So you can see it's a simple pulse train. So it's like 1 1 0 1 1 1 0 0 1 0 and so on. And so this pulse train is now biasing this ring modulator and altering the resonant wavelength. So now if you look at the output of the light that comes out of it, so you can see that this particular peak was the wavelength of this laser. But then as we encoded the electrical signal on top and we did amplitude modulation, you get these sidebands in the optical signal. And so that's how the optical spectrum now looks like, because the electrical signal is now encoded in these sidebands. And then now this optical signal goes through, and then this other ring resonator now receives the signal and decodes it, and then it extracts the amplitude information, the variation in the amplitude that goes through the photodetector, converts into electrical signal. This low pass filter is kind of like modeling the bandwidth limitation of this photodetector, because usually these photodetectors have some bandwidth limitation. So if your original information was transmitting at a really high frequency, the photodetector won't be able to convert that data as fast as the signal is changing. So use a low pass filter in series to model the bandwidth limitation of the photodetector. And then finally that signal comes out, and then we have this eye diagram generator, which can take in the pulse train that you're detecting at the output, and then create an eye diagram to see how accurately you can identify the 0 and 1 level at the output here. And so if we look at the output of the eye diagram, which is a very popular way to figure out like how accurately you can detect the 0 and 1 level. So here you can see that that's the 0 level and that's the level 1, and the signal is actually very clean. So as you're detecting your pulse train at the output, you can identify the 0 and 1 level very nicely. It's a very nice opening in the eye. So it's a very simple system. So it's working very efficiently. You can introduce some noise in your system and then see how this thing varies. For example, right now the laser source is an ideal source. If you want, you can introduce some noise here. So for example, we can enable the noise in your laser and then maybe even increase the noise a little bit and then rerun the simulation. And then now if we look at the eye, see. So now you can see some like it's still pretty good eye, but you can see some noise now because my laser source now has some extra noise. And so again, in terms of some non-idealities, you say that right now in this one, my bit rate is 25 gigahertz. If I want to crank up the bit rate, so let's see this is a pseudo random bit sequence generator. So this is simply generating a pulse train, and the bit rate is defining like what is the rate at which your information is coming, right? The 0 and 1, how fast they're varying. And this is one example where the expression is getting used. So in interconnect, the very top level is called the root element. And so in the root element, whatever parameter you have, you can actually use those parameter as an expression in any children. So any element that you have in your schematic, you can use a parameter from the root element to be a variable here. When you click on the bit sequence generator, you can see that we are using bit rate as an expression, and that's because the root element has the bit rate as a parameter. So this is simply the rate at which the 1 and 0 bits are changing in the signal generator. So if I change these to, let's say, 60 gigahertz, which is a really high bit rate, and then now I run the simulation again, because this photodetector has a cutoff frequency of 18.75 gigahertz, it should have trouble detecting signals that is coming at 60 gigahertz, 60 gigabit per second. So if we now look at the eye, we should see some more noise. And then so now you can see that the eye opening is really small. And that's because the bandwidth limitation of this photodetector is making it very difficult to accurately detect the 0 and 1 level. To be honest, for a practical device, this eye opening is still pretty good, but this kind of like shows you how you can account for the different non-idealities coming in your system and then kind of like figure out based on the output whether the circuit still works or not. Okay, so in terms of examples, going forward, we have now a bigger circuit, an optical switch. So an optical switch is simply a routing option in photonic circuits where you have an incoming signal, and depending on your choice of a control signal, you route the signal either on one output port or another. And depending on how big of an optical circuit switch you have, you can cascade multiple of these switches together, combine them, and then create complicated networks. And so this is where the hierarchical nature of interconnect comes in, because you can create a very big circuit by cascading these different switches together, put them inside compounds, and create a large hierarchical network. So here, for example, you have this compound switch, which actually is a combination of lots of 2x2 switches connected in sequence. So that's the basic building block. It's a 2x2 switch, which has some control signal. So light either goes straight through or it crosses from one input to a different output. And then you can combine multiple of these switches together to create a 4x4 or 8x8 or 16x16 switch, or even bigger networks. Another example would be another type of modulator. So this is a PAM4 system. It's an advanced modulation format where you can use Mach-Zehnder model was ring modulators. This one is a Mach-Zehnder modulator. And the way it works is as light comes in, you split the light into two paths, and then you introduce different amount of phase shifts on the two paths, and then you combine the light together again on the other end. Now, depending on how much phase shift you have introduced on each of these arms, as you combine the light again on the output side, you either get constructive or destructive interference happening. And so that way, the amplitude of the light at the output can vary. So you can imagine that you create one of these Mach-Zehnder, like you create these two branches, and if you change the phase shift of each of these arms based on the bit rate the sequence generator is generating for you, then you can actually control the amplitude of the light that's coming out of here. And that's kind of like the way that you control the modulation of the optical signal by using an electrical pulse train. So that's in very simple words how a Mach-Zehnder modulator works and how you can use this as a modulator in a system. So this particular example shows a PAM4 system where you actually use two modulators in series. And that way you can modulate multiple bits together in the same circuit. So here you have two modulators in series or two phase shifters in series. One takes in the most significant bit, and then the other one the least significant bit. So your information can be 0, 0, 0, 1, 1, 0, or 1, 1. And then based on that, you incur different amount of phase shifts in these two arms. And then so the output that you get can have, say, 4 different amplitudes for the 4 different bit sequence. And then you transmit that signal over a channel. And then on the other side, you detect the signal. And then you see what the eye looks like. So we can take a quick look at this example because, yeah, if you're interested in these particular applications, you'll see that PAM4 is a pretty popular modulation mechanism, just because it allows you to modulate your signal at a much higher bit rate. So let me just download that example. So it's the same circuit that we saw in the slides, light coming in, getting split. We have 2 phase shifters in series on the 2 arms. And then we have 2 pulse trains because one is the most significant bit, the other one is the least significant bit. And then you're modulating the light on the 2 arms, combining them at the output, and then you're detecting them at the end, and then you want to see the output. So again, we have an eye generator here to figure out like how good we can detect the electrical signal on the other end. So we can run this simulation. And then again, if we look at the eye diagram here, so now you can see the eye has 4 different levels because in a PAM4, since we have like 4 different combinations coming in to the modulator here, 0, 0, 0, 1, 1, 0, 1, 1. So that corresponds to 4 different optical levels. And so you can see that's like level 1, 2, 3, and 4. And again, like this is a pretty simple system with no error, no noises, and so on. So you can see the eye opening are pretty clear, and you can identify the levels pretty easily. However, like in an actual device, you'll have noises coming from the laser, you'll have noises coming from the modulators, from the photodetectors, and so on. And then so you'll have a noisy eye opening. And so this type of calculations become crucial. So yeah, I guess we're running out of time, but interconnect can be used for other type of simulation too. So you can simulate for lasers. So here are some application examples. One of them showing a DFB laser, distributed feedback laser, a DBR laser, or distributed Bragg reflector laser, and then I believe you have a Fabry-Perot cavity laser as well. So these are some examples, and these are some links to online examples. So if you just go to our example page and then search for laser. That should show you all the different types of laser simulations that we have. Yeah, so ring vernier laser and so on. So you can try them out if you're interested in laser simulations. And then finally, I had this slide here because on the first day there was some question about modeling biosensors. So this was the example that I was talking about. So again, like you can search for biosensor on App Gallery, and then you'll come up with this example. So the way this works is that you simulate a waveguide in FDE, and then you have a layer of an analyte on top, whose refractive index changes as you introduce the I guess like the biochemical that you're trying to detect. And then you perform an FDE simulation as the index of that analyte changes from one value to another. You figure out what is the effective index of the entire waveguide. And then the way you actually detect the changes in the index of the analyte is you create a Mach-Zehnder interferometer in interconnect actually, where one of the arm of that interferometer has a phase shifter that contains the phase shift of the waveguide as a function of the index of the analyte. So then you can run an interconnect simulation and then see how the amplitude of the light varies as you introduce some biochemical on the surface of your waveguide and the index of the waveguide changes. So then using this circuit simulation, you can select like, okay, so if the amplitude of the light is high, then maybe there's no biochemical or maybe no organic chemical are available or present near the waveguide. But then if there is something present that changes the index of the waveguide, and then maybe the amplitude of the light becomes 0. So that would be kind of like one way you detect or you use these biosensors in a photonic circuit. And yeah, that's it. I think that's all I had plans to show today. I know we are over time, but if there are any questions, I'm happy to answer them.
If you guys have any questions, you can ask our instructor. So
sorry, can you ask the question again? I think for some reason my internet connection is bad today. Oh, okay.
So there is a question in the chat.
Okay.
So there is a question in the chat. There is someone asked a question at 11 a.m. Is it possible to accommodate low dimensional structure? That question, sir.
11 a.m. The question about EG, right? Band gap niye je question ta seta?
Sir, previously 11:05 a.m. SM Saidujjaman Abir asked the question.
11.
Is it possible to accommodate low dimensional structure, Q dots, wares, or materials, MOS to WAC to HBN? And
sorry, AJ, is it possible?
Sir, I am
sorry, AJ,
yes,
a question to accommodate
yes,
low dimensional structures.
Yes, sir.
Right. Now, ওটা আমি যেটা বলছিলাম যে লো ডাইমেনশনাল স্ট্রাকচারের মেইন যেটা চ্যালেঞ্জ সেটা হচ্ছে যে চার্জে যখন আমরা সেমিকন্ডাক্টর ম্যাটেরিয়াল মডেলগুলো ডিজাইন মডেল করি, we use an effective mass approach and we use 3D density of states model for that. States তখন 2D and ওইটার I guess like the trend, right? There is I've seen people to use some effective index, like effective mass and some fitted band gap to try to model low dimensional structures using the the existing 3D model in charge. Kintu actually, to be honest, like that won't be very accurate. So yeah, when it comes to low dimensional structures, charge is not the appropriate solver. So that can be quantum nanotubes, carbon nanotubes, or wires, or MOS2 like graphene or MOS2. All of these cases, charge will not be the right tool.
Thank you, sir.
In terms of optical properties, however, FDTD you can actually model graphene. Grapheneer jonno ekta particular conductive model FDTD support kore. So at least on the optical side, graphene kora jay, and jehetu graphene kora jay, you can probably do MOS2 as well. But I don't think carbon nanotube is supported. But at least 2D material gulo supported in optical simulation.
Thank you, sir. Thank you so much, sir, for all your kind efforts and managing such a long period of time for us from your busy schedule. Here is a small
problem. I was happy to do this.
Here is small token of appreciation from all of us.
Sorry, yeah, voice abar atke jacche.
Sir,
but no, thank you so much for organizing this.
Sir, actually, sir, a COVID situation we are very lucky to have you as our instructor, because it wouldn't be possible if আমরা যদি এটা অফলাইনে অ্যারেঞ্জ করতাম, আমরা হয়তো আপনাকে ইনস্ট্রাকচার পাওয়ার মতো লাকি হতাম না। So we are very happy about that, and also we hope and pray to the Almighty for everyone's well-being. So our workshop ends here. Thanks everyone for joining and patiently learning this software with us. Hope you enjoyed this workshop as much as we did arranging it. Kindly fill up the form in the chat box, and thanks to our instructor, Dr. Ahsan sir again. We hope for your betterment and your family's well-being in this situation. The meeting will close in 5 minutes. I hope you all will stay with us in our future workshops. And if you have any query, you guys can fill up the form, write them in the form, or text us at in Facebook chat box in IEEE EDS workshop EDS page, or write them down in the workshop chat box. Thanks everyone.
Okay, sorry, আমার কানেকশন আসলে ঝামেলা করছে, সো আমি ক্লিয়ারলি শুনতে পাচ্ছি না সব কথা, বাট yeah, from my side, yeah, thank you so much for organizing this. এটা অ্যাটেন্ড করতে পেরে আমার খুব ভালো লেগেছে, and hopefully যারা অ্যাটেন্ডি ছিল তারাও আশা করি বেনিফিটেড হয়েছে কিছুটা। and again down the road যদি টুলস নিয়ে কোনো কোয়েশ্চেন থাকে বা কোনো এনকোয়ারি থাকে, আমাদের একটা ফোরাম আছে, Ansys forum, ওইখানে you can submit any question about our tools and features, and আমাদের application engineer will be happy to answer that. So feel free to use the forum, and yeah, যে কোনো help লাগলে আমাকেও feel free to reach out. I'll try my best to answer any question. So thanks again. আমি sign out করছি now.